All right, in our last video, we looked at what was called the combined gas law. And let's just go back and review that. We said that the combined gas law looked at a number of variables. Specifically, it looked at temperature, pressure, and volume. So let's make some notes here at temperature, pressure, and volume. All right. However, it omitted mass or amounts. Right? So it was a pretty good law. It combined Charles's law and Boyle's law, but it's still limited because it wasn't dealing with mass or amounts of gas. That's where this next law comes in. It's the ideal gas law. But to get there, we first have to start with something called Avogadros law. And Avogadros law is pretty simple, but it starts dealing with this missing mass and amount component. And so what Avogadros law states is that a given volume of gas always contains the same number of particles. And by particles, what I really mean is molecules or atoms. So in the case of oxygen, oxygen being O2 would fall under the molecules category, but there are some gases that are individual atoms, like the noble gases. So for example, helium or argon would be atoms. But what he found was that this would hold true under constant temperature and pressure. Oops. All right, so pretty simple concept. So for example, if you have a tank of argon that has a given volume, and it's at a given temperature versus a tank of the same size of helium, same volume and temp, then both of these should have the same number of atoms. So that was really the breakthrough here. But the main thing to think about, though, is if you think about argon versus helium, they have really different masses. If you look at the periodic table, argon is a lot heavier per atom than helium. So this was one of the big breakthroughs that Avogadros law basically found out, was if you just have a set volume of one gas, you're going to have the same number of molecules or atoms as the equivalent volume of another gas. All right. And here's the key component of this is he said that at 1 mole of a gas, it is always going to be equal to a set volume defined as 22.4 liters. And he said that this occurs at something called STP. So I'm just going to make an at STP. So you might be wondering what STP stands for. Well, STP stands for standard temperature and pressure. All right, so we know that the volume of a given gas can be impacted by temperature and pressure. So he said, well, let's just pick a standard set. That way we're not going to be dealing with changing too many variables all at once. And the standard temperature is always going to be 273 Kelvin, so not too far off of room temperature. And the pressure is always going to be 1 atm for standard temperature and pressure. So you may see this written out a lot, but it really simplifies a lot of the math that we'll use. All right, so now we've got a way of connecting volume and amount. So the next step was to take the combined gas law and incorporate Avogadros law to it. So we're kind of continuing to stack law after law after law. This next one is called the ideal gas law. And in my opinion, it's the most important gas law that there is. It's the most commonly used one. But what it says is that pressure times volume is equal to the amount of gas in moles, that's N, times our gas constant R times temperature in T. But that's okay, let's just label all of this. So this is going to be pressure. This is going to be volume. N is going to be number of moles. R is going to be our gas constant. And T is going to be temp. And like I said, temp is normally done in Kelvin. And the gas constant that we're going to use in this course is going to be based off of using temperature in Kelvin, number of moles, we're going to do volume in liter, and we're going to do pressure in ATM. So let's just define a lot of the variables here. So pressure, we're going to use ATM. Volume, we're going to use liters. Number of moles is just going to be mole. And then our gas constant, because of all these variables, is going to be 0.0821 liters times ATM, atmospheres, over mole Kelvin. All right, so this is going to be a really important gas constant that we'll be using with problems like these. I'll try to double check all of our exams and whatnot to make sure that I give you these constants. I don't expect you to memorize this one. I do want you to know Avogadro's number. That's really the only constant I want you to know. All right, so I'll show you something cool we can do with this. So let's do a cool trick with the ideal gas law. Obviously, you can do simple algebra, and if you're given, 3 of the 4 different variables, you could solve for the 4th variable. But I'll show you a trick that goes even further than that. All right, so let's think about this N value. So N equals the number of moles of gas. All right, and there's a lot of conversions that we've already done using moles. So for example, we said that if we have the number of moles of some sort of molecule or atom, that we can multiply this times grams over moles. So I'm just going to call this X grams over moles to figure out how many grams we have, right? Because then we cancel out moles, and we're left with our grams unit. Well, let's think about this though. This conversion factor, this is often referred to as the molecular weight, right? So molecular weight is basically going to be something that's grams over moles. That's the unit value. So units for molecular weight. All right, so pretty easy conversion, but let's think about a different one. Let's think about going the opposite direction. Let's say we have grams and we want to figure out how many moles we have. Well, if that's the case, we're going to do a similar conversion, but we're going to flip things upside down. We're going to say X grams over moles. Okay, so that means, yes, we've canceled out our grams, and yes, our units left over are going to be moles. But this time, what we're doing is basically an inverted molecular weight. So this could be referred to as 1 over molecular weight. So it's inverted. Okay, so this is where it starts getting cool. So if we take this, this is basically a tool for solving N, right? Because moles is equal to N. So let's think about it this way. I'm just going to take this down here, and we'll just slide it down here so we have more room. What we're saying is that we can take the mass times 1 over the molecular weight to find the value N for this reaction. If we want to simplify this even further, we can just say mass over molecular weight equals N. Okay, so this value right here kind of comes in handy because now we have another way of expressing N. If we have the mass of the gas, we can plug that in. If we have the molecular weight, we can plug that in. So both of those could be plugged in lieu of just inputting the number of moles. Okay, so let's think about how this could apply to our PV equals nRT equation. So PV equals nRT is the ideal gas law, but now let's swap. Okay, so if we do this, that's going to mean that we've got PV equals mass over molecular weight times RT, right? So we're just doing some algebraic manipulation. But what this allows you to do is we can solve for this variable. If we know everything else. Okay, so let's just try to rework this and let's try to clean this up. So let's try to get molecular weight on one side of the equation. So if we want to do that, we can multiply both sides by molecular weight. So I could say PV times molecular weight is going to be equal to the mass times RT, right? So that's what's going to be left over. And that means we could say, well, molecular weight would be mass times RT over PV. And oftentimes you'll just see this abbreviated as M. But I'm just going to keep it as mass right now so we can kind of keep track of everything. Okay, so we've got this really nice tool for finding molecular weight. Whoop. So let's try to put this in the context of a practice problem. So let's imagine this problem. Let's say we've got an unknown gas that we're investigating. So this unknown gas that we're investigating has a mass that was determined experimentally to be 3.35 grams. It has a volume that is equal to 2.00 liters at 1.21 atmospheres, that's the pressure, and 27 degrees Celsius. All right, what is the molecular weight of the gas? Okay, so let's try to do this on our own. So we said that molecular weight is going to be equal to mass times our gas constant R times our temperature T over pressure times volume. So let's start plugging things in. So we said the mass is going to be 3.35 grams. So we got that part. R is a universal gas constant, 0.0821 liters times atmospheres per mole Kelvin. All right, so now we've got the R done. And then for temperature, we've got 27 plus 273 because we need to make sure that this temperature isn't expressed in Kelvin or in Celsius, but rather in Kelvin. That's why I'm adding the 273. All right, so we've got that part taken care of. And then on the bottom side, we need pressure. We said it's 1.21 atmospheres. And we said that its volume is 2.00 liters. All right, so if we plug this all in, our final answer that our calculator spits out at least is 34.09524. And we know that the units for molecular weight would be grams per mole, right? Okay, so that tells us the molecular weight of the gas. However, we need to be careful with sig figs. All of these measured values up here, right here would be 3, right here would be 3, right here would be 2. So I would probably go with 2 as my significant figure, and I would just say that this would be equal to 34 grams per mole. That way I'm following all of my sig fig rules. All right, this would really narrow down the identity of the potential gas and can be used by chemists as a tool for identifying any sort of unknown gas. It's a really kind of clever trick, and I think it's neat because it's just a variation on this simple PV equals nRT equation. With that being said, you can do a lot more with the PV equals nRT. Like I said, if you have 3 of the 4 constants, or sorry, 3 of the 4 variables, you can solve for the 4th one by using just simple algebra. However, remember, in order for this to work, you have to have the correct units so that everything cancels. In fact, let's go back to that last problem and double check that everything cancels. So if we look at this last problem, we can cancel out atmospheres right here, right? Because we got it on the top and top. We can cancel out liters because we've got it on the top and we've got it on the bottom. And then over here, we've got Kelvin and Kelvin. But you see how the units left over are grams as a potential numerator and then moles as a potential denominator? That's why we had the proper units left over. So this was just using, clever tricks of algebra. All right, I know this can feel pretty overwhelming. I will say with most of these, the best way to practice them is to just go through book problems, check your work in the back of the book, try to study with a friend, go to the SI sessions, try to get as many curveballs thrown at you as possible. That way you feel really comfortable doing all of this algebra, because I know sometimes it's a little bit tricky. All right, good luck studying, and let me know if you have any questions.